Hello students, welcome back. We completed everything except 3.4. But before starting 3.4, let's have a brief recap. Really brief. I'll try to be really brief. We define the modulo order like this. The smallest positive integer n such that a to the nth power is congruent to 1. And this is well defined if and only if a and m are relatively prime. So under this assumption and under this definition, we have these properties of the modulo order. First, the divisibility property 1.2, and the distinctness property 1.3, and finally the GCD property 1.4. Remember all those? You should. They're all important, including their proofs. So remember all those. 1.2, 1.3, and 1.4. We'll use all those. And then in section 2, we define the primitive root. The order of a modulo m happens to be phi of m. That's when a is called a primitive root of unity, modulo m, or simply a primitive root of m. The question is, how many are there? Well, it turns out phi of m, incongruent primitive roots of m, claims 2.2 if there's one to begin with. Oh, if there's one to begin with, what do you mean by that? That's what you mean. Primitive root exists if and only if, and we have this complete solution. But the problem is we can't prove it. It's too difficult for us, so we're going to prove only a special case. We'll prove that primitive roots exist modulo prime. So in section 3, we consider mod p only, no more mod m, and the first topic, Lagrange theorem, is based upon mod p, as you can see. And then its corollary is also based upon mod p. P is prime, and d divide p minus 1, pay attention to this especially. Then, actually d power is congruent to 1 mod p, has exactly d incongruent solutions. Remember this corollary because we'll be using it. Let's go back to 3.4. So what does it say? Just like the condition of 3.2 corollary, we have this condition, p is prime and d divide p minus 1. Then they're exactly phi of d incongruent integers with order d mod p. Before proving this, let's discuss its immediate corollary. In a special case, if we put d is equal to p minus 1, in general d divides p minus 1, but in a special case when they are the same, then we can replace d by p minus 1 in this conclusion part. So p minus 1 goes here, and then also here. So what do we have? The order of a mod p is p minus 1, but p minus 1 is phi of p. So the order of a mod p is phi of p. That means it's primitive, a primitive root of p. And how many are there? Phi of p minus 1, but p minus 1 is phi of p. So we have phi of p. So it's as expected. So we prove that primitive roots exist modulo prime, and precisely as expected, phi of p. There are that many. Alright, so much for the corollary because it came immediately from the main theorem, so let's not worry about the corollary anymore. Let's go ahead and prove this main theorem. We're going to take multiple steps here because it's going to be a difficult proof. First, we begin with the preparation. Define psi of d as this. Begin with this set. A subset of whole numbers less than p. The Zp is set of whole numbers less than p. So 0, 1, 2, 3 up to p minus 1. 0, 1, 2, etc., up to p minus 1. And then among those, A has the order d mod p. So in short, the number of elements of that set means the number of whole numbers less than p with the order d modulo d. That's what it means. And then, due to the division algorithm, every integer is uniquely congruent to one and only one element of the p mod p. You see, divide by p and take the remainder, and you're gonna get one and only one from some zp from 0 to p minus 1. Therefore, any integers can be reduced to a remainder in zp modulo p, so we can make this conclusion. Phi of d is the same as the number of incongruent integers with the order d mod p, the precise quantity that we are looking for, and this theorem claims it's phi of d. So in other words, this is what you have to prove. Psi of d is same as phi of d if d divides p minus 1. You see? That's the condition. So that's what we have to prove. Okay, how are you going to prove it? First, let's prove a special case. D divides p minus 1 as before, and C of d is greater than 0, then C of d and phi of d are the same. What do you mean by psi of d is greater than 0? Let's go back there. That means this number of elements is greater than 0. That means this set is non-empty. In other words, there should be at least one A with order d mod p. There should be at least one whole number less than p with the order d mod p. And that is, as a matter of fact, equivalent to there exists at least one integer whose order is d mod p, because we can take mod p by the division algorithm. So in short, this definition here, which I highlighted in blue, is kind of like the one in 2.2 if there is one to begin with. There are this many incongruent primitive roots of m if there is one to begin with. You see that one, which I just highlighted in blue? That corresponds to this condition, if there is one to begin with. If this is non-empty, which is such an A exists. So let's go from there. There is at least one integer A in ZP with the order D. There is one to begin with. For this A, we have this property. A to the D power is congruent to 1, of course. Order is D. And then this D is minimum, so 0 power, first power, second power up to D minus 1. None of them is congruent to 1, but also they're all distinct modulo P. Remember this? The distinctness property 1.3. And also another way to write the same thing is write like this: up to A to the D power and then dropping A to the Z power. If this is more convenient, you can do it this way too. Either way, A to the 0 power and A to the D power are both 1, so either way is the same. But me, most of the time, I keep 0 and then discard the last one. But sometimes the latter is more convenient. In that case, I'll not hesitate using the latter. So what do you have? We have A to the D power is congruent to 1, which is a solution of this. X to the D power is congruent to 1. And then A to the 0 power, first power, second power, they're all distinct mod P. Yeah, they're all distinct. But not only that, they all satisfy this congruence. Look at this. A to the H power to the D power is A to the D power to the H power, so 1 to the H power, so it's 1. So all these satisfy this congruence. They are precisely D solutions here that are incongruent, and they're all incongruent. They are all distinct mod P, satisfying this. So what does that say? This covers all possible solutions. You know, by the corollary, they are precisely D incongruent solutions, and we do have D incongruent solutions here. So they cover everything. They cover all D incongruent solutions. So the final question here is, among those total of D possibilities, which are completely covers from A to the 0 power up to the A to the D minus 1 power, or equivalently, a to the first power to a to the d power. Either way it works out. Both are correct. How many of them have order d? That number is defined as C of d, and we're going to claim that it is equal to phi of d. Alright? Among them, how many have order precisely d? You see, a to the d power is congruent to 1. That means the order divides d, not necessarily equal to d. Remember 1.2, the divisibility property? Only a few of them may be just having the precise d as the order. When? Well, we can use 1.4, the GCD property. The order of a to the h power modulo p is the order of a over the GCD of the order of a and h. Remember 1.4, the GCD property. And it is equal to d if and only if the denominator is 1. So we are looking at the GCD of h and d is 1. And then let's go back to this. Among the powers 1, 2, 3, 4 up to d, how many are relatively prime to d? In this case, going 1 through d is more convenient than 0 to d minus 1. We have the precise definition of Euler-Phi function. So it's phi of d. So there are that many with order precisely d. So c of d and phi of d are the same. Under this special condition, which is highlighted in blue. Anyway, we proved the special case. Under this special condition, phi of d and c of d are the same as expected. Now, are they the same in general? Let's go ahead and prove that, and that's step 3. So in summary, this is what we did so far. Under this special condition, we did it. In general, however, we don't have the equality. We have only the inequality, semi-inequality less than or equal. The reason? When c of d is 0, then that's less than or equal to phi of d. Otherwise, they're equivalent. They're all the same. So in general, we have only inequality. Now, let's apply Fermat's theorem. For any whole number less than p, a to the p minus 1 power is congruent to 1 by Fermat's theorem. And then apply the 1.2, the divisibility property. A to the p minus 1 power is 1, so the order of a is a divisor of p minus 1. And all these numbers satisfy this, so it'll have, the order will be a certain divisor, and consequently, in the opposite viewpoint, if you can regroup all those and then add them up, we're going to get the total of p minus 1 back. For each divisor d, get the number of all the a values that have precisely the order d. So it is just counting everything after regrouping, and this is counting straightforward. Either way, we have to have total number of elements, p minus 1. And then, let's compare that with Gauss' theorem, which we proved in lesson 11. P minus 1 is equal to the summation of phi of d. Compare these. Summation of phi of d and summation of c of d must be the same. But then again here, c of d is less than or equal to phi of d. And I claim they have to be all equal, because if there's any one strictly less than phi of d, then there's no way to catch up, because everything is less than or equal to phi of d. So unless they're all equal, you kind of have the sum that are equal with something strictly less. They have to be all equal. In general, c of d and phi of d must be the same if d divides p minus 1. You see, d divides p minus 1. They come down here, there, there. That completes the proof. C of d and phi of d are the same in general as long as d divides p minus 1.